It's good. It's right at the hour, so I can have the first recording 1 hour and the second recording another hour. It's perfect.
Everybody
Hi.
has to miss our fun introductions to each other, though. We got to chat mask free. It's wild.
Yeah.
I know it's so, yeah, it's so different this year. Usually I know all the students by the second week of class. Now with the mass, and let's say I have two Katie's and two Jean in the class, and I have Emily and Jean, they look a little bit like each other. I'm I'm not able to differentiate all the students. Anyway, okay. Steve, nice to have you here. Do you have questions?
Yes, I do. Am I jumping in front of these other people?
No, what we were doing, we were just going over whatever questions they had, and they were here to hear other people's questions. So that was what we're doing, and also we were going over some exam question from last year's exam. So we were just filling up the time with stuff.
Okay. I guess my excuse me, my question is in regards to the isoflurane lab.
Yes.
And I was just, when you were explaining it in class, I was understanding, I thought I was taking good notes, and then 3 days later, I worked on my lab report and my notes didn't make any sense to me. So I guess I'm just having issues interpreting some of the data on these, like for instance, the, I don't know if you remember all your labs, but like the co-elution, like, are you always going to have two products when you have two parents eluting? Am I looking at that incorrectly?
Oh, so is it the LCMS lab that you're talking about?
Oh, yes,
Yeah.
I'm sorry.
Yeah, so the isoflavones LCMS lab. Okay, so yes, when you see two parent ions that are not related, like for example, in that I think what I remember was genistein and malonyl diazine, parent ions or precursor ions. These are, when they hit the ESI, they never convert families. They're from two different families. So if you know a little bit about their chemistry, you know that they will never become another family member. They will not cross family lines. So if you see two compounds that are not related to each other in terms of their molecular formula, then you would say, oh, I have two distinct compound reaching my detector at the same time. So this must be a coelution. So when we know that they cannot cross families, we know that when they hit the ESI and went into mass detection, they are two different components coming out at the same retention time. So if they're coming out at the same retention time, that means they are co-eluting.
Okay.
Yeah.
Okay, that makes sense. And then
you see two different product ions because each one of them partially fragments when they hit the ESI. It's soft ionization, but weak bonds can be broken. So you see a product ion for each one of them, and you see the entire molecule. So not all the molecules, all of these molecules broke at the glucose. Some of it did break at the glucose bond, and some of it continued intact. So that's why you see two parent and two product ions.
and then can you tell that on the like on the main one? Are you able to determine, like, I know with like
No, when you see the chromatogram, the total ion chromatogram or the select ion chromatogram, it's like looking at the chromatogram from HPLC and UV detection. You see peaks only. You don't see a spectra. You're just seeing the peaks that are coming. Your y-axis is either the absorbance or relative abundance, and the x-axis is the time. It's not the spectra or the absorbance or the mass. So all you see is a peak, one peak coming at that one time. So you can't tell if there is coelution or not. when you open the spectra, you saw, oh, these are not related. So these are two different compounds. So yes, there is a coelution. So that's an example how MS is powerful in a sense that even if you see a chromatogram with certain peaks, that doesn't mean each peak is pure. The MS is going to tell me what's the composition of this peak.
And
You
then
can do quantification when you have two peaks or two compounds coming in one peak, you won't be able to quantitate each one of them, but you can detect the presence of both of them. So you can do qualitative analysis and identification analysis. But if it came down to quantitating, you'd say, no, I have to go back to my chromatography and make sure these two peaks, there's two compounds split into two peaks, then I can do quantification. So I go back to my method and see how am I going to adjust my gradient to get better selectivity. And when I have better selectivity, I have better separation. And the MS can confirm that when I separate these two peaks, yes, this is genistein, this is malonidides, and now I can do quantification.
And then that kind of leads into my next question is, excuse me, further down, there's a isomer on, and it appears that in the main chromatogram, it kind of appears as like two little bumps right before the big one.
Yeah, so the isomers that we looked at is one little one that came just before the big one. These are the two that we looked at the spectra for.
And that as well, that's the same kind of deal. You can't really confirm that unless you actually dig deeper and actually look at the.
Yeah, this is a different case of coelution. This case is you have two peaks that were not coeluted, they were separated, and they're giving you the same mass. So now you have a problem because the MS is telling you this is malonyl-genistein and this is malonyl-genistein, but hey, they're not. They're coming at two different times. They can't be the same molecule. There must be something different about these molecules that made them separate as they eluted. So the MS didn't tell me what they are. It just told me these are isomers because they have the same mass, but they eluted slightly separated. So the only way I was able to tell you with confirmation, this is 4 double prime and the other one is 6 double prime, is because we did NMR on it. The MS didn't help me. I had to take those two individual components, collect them and do NMR, and NMR told me where the function group position is. One was at the 4 position of the glucose unit and the other one was at the 6 position of the carbonate in the glucose unit.
Okay. And then I feel like you were able to tell, I don't know, I don't remember the verbiage you used, but like out of these two isomers, like one was more dominant, is that?
Yes. So the one is more dominant in nature. So isomers, there's always more dominant isomer and less dominant isomer. They're just isomer. This is how it is. So the one that is more dominant, you see that it on the chromatogram, it has a larger peak. So in nature, there's more of it.
Okay.
And the other thing is that we saw that the MS gave us is when we looked at the spectra, the molecular ion had lower abundance in the less stable isomer. So you had more abundance of the molecular ion in the other one. So that told me that it was weaker. The bond was weaker for that one compared to the other. That's the only information that the MS told me.
Okay. And then if we go to like the next one, right, following the isomers, and there's no product.
Yes.
So my question on that one is, there's a bunch of smaller ones, but how did you know that like not like the tallest one of these smaller ones was actual product?
That is, no, actually, you want to remember the product always have lower molecular weight than the molecular ion because the molecular ion is the parent, right? When it breaks, it can only be smaller. It cannot be bigger. So that's always, you want to remember that. Second, as an analyst that you have experience, and then you have your instrument, and you know the limitation of your instrument, then you'll know which ones are noise and which one are real. Because with every instrument there's noise. Noise meaning you get some signal, but it's not really real signal. It's carry over, it's instrument noise that you just know because you've been very intimate with your instrument. You've
Okay.
ran it multiple times, you've ran blanks, so you know which is noise and which is not. So when I tell you ignore the little peaks, that's because we know our instrument and we know that these are noise.
Okay. And then the very last one there, I'm assuming it's kind of the same. There's no fragmentation.
Yes. So these are the, if you remember the structure, if you have your lab manual open in front of you to page 99, it would be good to grab it. Go grab it.
Okay.
Yeah.
Got it.
Okay, so if you open to page 99, look at the first structure, the aglycone structure. It doesn't have a sugar. So in nature, you have aglycones, you have these structures present. So in your extract, you have those. But because they don't have the sugar, they will come out later because it's reverse phase chromatography. So they will be more or less polar than the others. So these are the ones now, when you see them coming out later, these are the naturally present aglycones in your actual extract. So, and you don't have a glucose, you don't have weak bonds anymore. So you just see them as is. So these are the molecular ions. Whereas the ones that were coming up before, they had the sugar. So they were more polar. So they come out a little earlier, and the sugar bond is weak bond. And so some of it is being cleaved off to give you an aglycone. So the aglycone in the previous ones were product ions, but the aglycone that is coming later on in the chromatogram, these are the actual aglycone present in your sample. At that point, they're starting to come out.
Thank you.
Yeah, does it make sense now, Steve?
Oh, better.
All right, better. Good. Yeah, digest it a little bit, and
Mhm.
if you need more explanation, happy to.
Okay. And then another question was, I know you said we're going up to IR.
Yes.
So that includes this lab and the atomic absorption.
Yes.
And then that's the cutoff atomic absorption.
Lab.
Great.
But
Okay.
we have the IR lecture that I posted. You got to
Yep.
review that. Yeah.
Okay. Okay. I think that was it for now.
For now, good. Did anybody else come up with additional questions, or do you want to still continue with the exam questions?
I do have two additional questions for
Yeah.
that. So
Yeah.
One would be, I noticed on on the exam, it doesn't specify that for the question, let me find the question number. It's the LCMS one, or HPLC MS question number 3 on the 2019 exam.
Yes, okay.
It doesn't explicitly state that it's reverse phase. Are we supposed to be able to interpret it as reverse phase just based off the order of the spectra?
Let me see.
Or maybe it's not reverse phase, I don't know. But
it is reverse phase because you've done the lab and I told you it's reverse phase. So take my word for it.
okay.
So just remember it is reverse phase because I told you. So yeah, it is the same. It is the same lab, right? So
Yep.
it is the same chromatogram. So you want to remember that.
Okay. the other one I had was if we could go over internal and external standards and when you would want to use one or when you would need one to be quantitative or qualitative.
Okay, so internal and external standards would be great to have when you want accurate quantification, especially when you have sample preparation that have multiple steps. So there could be a lot of losses. So internal standard is key there to have accurate quantification. If you have to have quantification point, whether accurate or not accurate, but you want to quantitate, you need external standards. You need to plot your standard curve or know their signal factor. If you have a signal factor for each standard, you don't need to plot a standard curve. That's complicated, forget about it. But in order to quantitate, you need external standards. That is 100% all the case. When you hear quantification, you need external standard. When you hear accurate quantification, you need both. Okay, because the internal standard job is not per se to quantitate, but it's mostly to correct for losses. You would add it to all of your standards and the external standards. So that internal standard is added to the external standard solutions, and it's added to the samples, and it's added in the same volume and concentration. So you would have a stock internal standard solution, and you'd add the same volume to all of your standards and all of your samples. So when you do that, so when you're preparing your sample and you have internal standard from the beginning, from the get-go, any preparation steps that might cause losses, evaporation, losses in transfer, anything, the same loss is going to be applied to the internal standard. So you're correcting for that loss. So you have better, more accurate quantification. So just remember in your head, quantification, external standard, accurate quantification, both. Yeah?
Okay, thank you.
So can you guys remember the characteristics of internal standard? This is a common question that I like to ask. What characteristics you should have of an internal standard?
I think you had mentioned that you want it to be similar to what you're looking for, but not actually present in your sample.
Exactly. So chemically related, so structurally related to your components, but not present in your mix. And also not only that, it elutes separate from all of your components and within your analysis time. You don't want to increase the analysis time. So you don't want something that will come out half an hour after all of your sample components came out. So these are your three main points here. Similar structure that is similar, does not co-elute with any of your components, and also elutes within your analysis time. So these are three main characteristics that you always want to keep in mind when you select your internal standard.
Real quick, I was just curious, since the labs, the atomic absorption and the soy isoflavones are going to be possibly on the exam, and we haven't got our lab reports graded yet, is it possible to get the sample lab reports for those?
Oh yes, thank you for the reminder. I was going to post this up today because yesterday at 5 was the last submission. So I will put the key of the questions for both. Let me open now so that I do not forget this. So yes, I will post the key for AA and MS, and I can, do you want the example sample, or the key for the questions is enough?
The key would be great because I definitely think I bombed the isoflavone one.
Okay.
I did better on the atomic absorption. I guess I took better notes.
Okay, good. So I will post these two right now as we speak. I love Dory. I am Dory. I have a short memory loss. So I will definitely do that right now. But
Okay.
you can think of more questions while I do that.
Okay.
Or ask questions.
There is a question on the last year's midterm about decaf, seeing if the caffeine or measuring the caffeine content in the coffee. And one of the questions it asks is examples or sources of error that could lead to under or overestimation. Are there
Yes.
any like
Can you
responses to?
tell me which question that is? Is that on the exam?
Yeah, that is last year's midterm question number 4, part D.
Okay, part D.
Part
Number
D.
4.
Yeah.
Part D. Okay, so you tell me there is plenty of sources of error that could potentially lead to under and over. So don't list the errors, just listing them, but you want to say which ones will cause under, which ones will cause over. And I say list at least 4 errors, either direction. If you list all errors for overestimation, I don't care. Just list 4 potential error and tell me which one will be over and which one will be underestimation. So that's good discussion. So you guys can think of errors and tell me. Sam, what you asked that question?
Well, I guess the first thing that would come to mind is just like sample loss. So if you didn't have an internal standard and you lost sampling, you wouldn't know how much you lost there. So that could lead to an underestimation.
Very good. But let's say that's a good question. That's a good answer. It might not be one of my key answers, but if you get deducted points for such an answer, you come to me directly. It is a correct answer. Okay, what else?
Isn't that the lab where we had to we had to separate the protein and dairy from the mixture?
Yes,
So
exactly. So we
that-
use pepsin. So so we used an enzyme, a digestive enzyme. If you don't remember pepsin, just say digestive enzyme. That you don't have to say pepsin specifically. You can say that is correct. So if the digestion was incomplete or was not done, you're definitely going to get an underestimation because the caffeine will be bound to the protein. It's an alkaloid. You don't have to say that, but it will be bound to the protein. And if you don't break up the protein properly, it will be filtered out with the protein. And it won't be in your little extract tube vial that you use to inject. So that's definite underestimation. Okay, very good. See, so you already got 2 right there. Okay.
Is that one okay, even though the question's asking about the decaf coffee and not the dairy coffee?
Ooh, I didn't
Oh,
see
yeah. Oh. Won't you have milk sometimes in your decaf coffee?
No, I don't drink decaf coffee, first of all.
Yeah, but usually people might add dairy to decaf coffee, so it's okay. Did I say non-dairy? No.
No, you just said decaf.
Yeah, decaf coffee. So I will still consider that as a. So if you say that answer, you want to say if there is cream or milk in your sample, then that is a potential. Just make sure you say if there is milk. We don't know. I didn't tell you there isn't any. It could be. We didn't do that in the lab. We had another dairy coffee and 1 decaf just to not to complicate. I wanted to have decaf separated from another source that had caffeine, but with dairy. It's just for the purpose of you seeing different samples. But this question, yeah, you could have milk in your sample. So that is still a valid answer. Okay, good. What other, now these are both underestimation. In what case you might have overestimation?
Isn't there certain compounds found in coffee that interfere with the reading? Something like, I forget the word, phenolic or something like along
Yeah.
that.
Perfect. Yes. And you
Yeah,
actually
coalition.
saw that in the lab. You had the decaf coffee and you had multiple peaks coming together. And actually, the peak that we said it's most likely the caffeine was not pure because the spectra had another shape than the actual standard. So your peak might not be pure because there are other phenolics that could coelute with it. That could lead to overestimation. Yes, very good. Dilution errors, guys, dilution errors that can go both ways. If you over dilute or under dilute just by pipetting, that could lead to either underestimation or overestimation, depending on your laboratory skills. So that is very easy to remember, dilution. So you have the spilling, potential losses, dilution errors can go either way, the presence of dairy, not pure peak. So these are all another one, which is a creative answer. Some of you might be creative that way because I did mention it too in class multiple times, is if your concentration lies outside of your standard curve. So we have a linear standard curve, right? And if your concentration is above the highest concentration of the standard curve, you don't have any power of prediction there. Or it's if your sample lies below the lowest concentration of your standard curve, it also you don't have power of prediction there. So, and it could either be over or under. That doesn't matter. It depends on the compound itself. So if you're outside of your standard curve, you may over or underestimate. It can be either way.
Is
So that,
there? Oh, I was sorry. I was gonna say something else relating to that though. But
yeah, go ahead. I'm done.
okay.
Yeah.
Is there a response to that question that could have to do with the detector that's used? Like if the detector is not set to the right
Yes.
wavelength or something?
Yes, if let's say you did, that's a good question, Sam, but I won't be expecting you to do to answer that way because it's more advanced. So let's
Okay.
say you did your standards on Monday. You had your standard curve on Monday and your detector was working fine. And then you came on Tuesday or Wednesday, same column, same everything, you didn't change anything. You would say, I still can run my samples. The lamp, something happened to the lamp and it's under its efficiency. You'll get different signal, you'll get reduced signal just because the intensity of the lamp was reduced. So the lamp was dying. It was good on Monday, but on Tuesday and Wednesday it is dying and you don't know that. So you will consistently get underestimation and you won't know unless you know where the range of your concentration is and you're consistently getting lower. Then you would go, oh, something's off with this lamp. And then that means you need to change the lamp of the detector. Yes, so
Okay.
the detector can go bad anytime and will change your signal anytime. So that is something as an advanced analyst, you would then, it would be one of your troubleshooting. Yeah. But I didn't talk about this in class, so I don't expect you to know it. But if you're a graduate student, let's say, and you already know these things, or you're Sam that works in our lab and already is exposed to a lot of graduate school student and analysis, then and you answer that, it's not in my key, but it is correct.
Okay. Thank you.
Mm. Okay, so while you think of other questions, I'm going to post the key right now for these two labs.
Could you go over 5C on the,
Yes. Five.
it's the question about the iron and calcium, and it's regarding the,
Yeah.
is the excitation energy electronic, vibrational, or rotational?
Yes. So what do you think it is, Stephen or Steve? So you want to know, you want to go back to that intro to spectroscopy lecture where we talk about what is electronic energy, what is vibrational energy, and what's rotational energy. If you know the difference among these three, and then if you know that in atomic absorption, you're actually analyzing atoms in the gaseous state, that means they don't have any chemical bonds. So they are singular atoms. And if you know that electronic energy is, okay, I saw a shadow of my dog outside. Okay. So if you know that electronic energy is only that valence electron in an atom that goes from one shell to a higher shell when it's excited, and if you know that vibrational energy has to do with the bond, with the stretching and bending of molecular bonds, and if you know that rotational energy has to do with rotation around in a molecule around its gravimetric center, you'll know that there is no vibrational or rotational energy in your atoms. So you know that the answer is electronic energy. And then you have to explain why did you say electronic. Again, before you joined, Steve, I was telling the others that look at the points distribution. If there is 5 points allocated to question C, if you just answer electronic and leave it there, you're not going to get the points. You're going to get partial points. You're probably going to get 1 or 2 points. You have to explain. Don't assume that I know what you know. I need you to show me what you know by writing it down. So explain. Look at the points distribution, and from looking at the points distribution, you say, I'm sure she's looking for more than just one word answer for a 5-point question.
Yeah, I've made that mistake in pre-lab quizzes. Only
Yeah.
giving a very short answer. So.
Yeah. Yeah. I mean, it's kind of a personality thing. Some people are very concise and they're smart and they know, okay, I know this and here's the answer. It's concise. But in an exam or a quiz, we really need to know if you know. And the only way is to write out what you know and don't assume that we know what you know. Yeah. Okay. So let me one more to go in uploading the key. All right. They're there. Now the key for AA and MS is on Canvas under lab report questions key.
For 5E on that same question, it asked if it could read 2 minerals at the same time. I feel like I remember a lamp that had 2 minerals. Is that?
Yes, so the calcium lamp, I think it does calcium and magnesium. So if a lamp, so it depends on the source of, well, first, are you doing AAS or are you doing ICP AES? If you're doing AAS, the only correct answer would be, well, you might say no, because each lamp has one cathode of that metallic form of the element. But you can say yes, unless that lamp has 2 cathodes, example, the calcium and magnesium, lamp. So then you can do two element detection without changing the lamp, but that's not simultaneous. Why it's not simultaneous in an AAS is because you have the photo multiplier tube detector and you have a monochromator. That monochromator is selecting one wavelength at a time. So you can only select one wavelength for calcium and measure it, then switch to another wavelength and then measure the magnesium without changing the lamp. Okay. So it's not simultaneous, it's sequential in this case. But if you're talking about ICP, yes, you can measure simultaneously if you have the Ischl detector or if you have a detector that has multiple photo multiplier tube detector that can read at the same time. So you need to be very careful in how you answer and to clarify your answer in different conditions, under different conditions.
Thank you.
Yeah. So if you're doing atomic absorption, so my answer, the correct answer to this question would be no in atomic absorption, because you don't have simultaneous. You can have sequential only if you have a lamp with multiple cathodes. Okay. Think about more questions. I'm going to hop to the bathroom really quick and I'll be right back.
Have any of you asked about the bonus question yet on the?
Oh, not really. We had one quick thing about IR, but I think it'd be good to ask about that. Also, I might ask this, but I was wondering if IR was the only approach we had that doesn't excite electrons. I don't know if there's any others, but I know it doesn't. I don't know if that matters. But. I can ask that.
Good question. I don't know the answer.
Chris, do you remember, or did you write down the balance number that we used yesterday for vacuum?
Yeah, number 4.
4, that's right. Thank you.
All right, I'm back. Do you have any other questions that came up? No?
One of the ones I had was, so we mentioned that AA and UV vis are definitely exciting electrons. But or unless if that's not right, but
Say that again, AA and?
UV vis, those excite the electrons, right?
Yes. Well, AA is absorption, right? So atomic absorption or atomic emission. So whether it's absorption or emission, it's in the UV vis range. And the UV vis range is excitation of the electron, whether it is in an atom or a molecule. It's excitation of the electron. Yeah.
And then on the flip side, is IR the only one that doesn't excite electrons and only does the bonds?
So IR radiation, the infrared irradiation, is the radiation that has the energy, what do you call it? So the energy levels that match the vibrational allowable energy levels. Yes. So yeah.
Okay. All right. Thank you.
Yeah. So you want to remember your in food analysis, you mostly only use UV range, visible range, IR range. So these are the ranges where most, if not all of the analysis is if you're using spectroscopy. So yes, IR is vibrational and UV vis is the electronic.
I'm sorry, what was the third one you mentioned? You said UV, IR, and what was the other one?
Visible. So the UV range, the ultraviolet, then you have the visible range, then you have the IR. IR is of lower energy levels than visible, than UV, and it has to go with the wavelength of that range. So the higher the wavelengths, the more the energy. So UV is higher wavelength than visible, and visible is not higher wavelength, higher energy, sorry. So the UV is higher energy, shorter wavelength. Visible is lower energy, longer wavelength. IR is even lower energy and longer, longer wavelength, yeah. Just a second, my dog.
Could we talk about the bonus question,
Oh yeah,
please?
yes. Let's look at the bonus question. Okay. So what would you want to know? What do you think this is? So that comes from that makeup lecture. It's the exact spectra that I show in that lecture. So what the question is asking you here, this is the spectra of butylaldehyde. What type of spectroscopy is this spectra coming from?
Are you asking me?
I'm asking everybody.
Sam mentioned IR earlier.
Yeah, you want to be specific here. Is it mid-IR or near-IR? That's when you need to study that lecture. So it is a mid-IR spectroscopy. So don't say just IR, you'll get a partial point. Actually, specifically, I would say it's, if you say mid-IR, you get 3 points. If you say IR, you'll get 2 points. So you want to be specific in that. And then you want to explain, I don't need to know the range difference. I know there's a range difference in mid IR and near IR. I'm not gonna tell you what's the length of what's the wavelength in each region. I don't want you to know that. Good information for you to know, but no. So I would want you to explain to me what it's based on absorption of light in the IR region. Simple, say it. You might think this is simple, but just say it. It's based on the absorption of light or energy in the IR region. You want to say that. You want to say that it's vibrational energy. So you want to say it's based on absorption of vibrational energy, which is based when you absorb IR energy, your bonds are going to vibrate in a stretching mode or bending mode. Just say that. And then what does it say? Also, the question asks, what type of spectroscopy? Briefly explain the principle of the spectroscopy method. That's it. That's what I just said. And then state at least 2 applications. So now you can state 2 applications. You can say structural identification, that's one. You can say a fast quantitative method for determining, let's say, composition in milk. And that is a common example that I gave during that lecture.
Thank you.
So another important thing to say for that question is that your functional groups, the different functional groups, are absorbing in different regions. Hence that you see here in this image, in butyl aldehyde, every different functional group is absorbing a different wave number. So you have, the bond C double bond OH is absorbing somewhere different than where you have C double bond O. So from that image, it's good to say that different functional groups absorb at different regions. So that's another thing you want to point out. So you want to look at your image and try to decipher what the image is showing and make sure you write that down.
Okay, thank you.
And that's a bonus. So, that's extra credit. So try to get as much as you can from that bonus. 10 points out of 100%, that's something.
Did we ever mention what near IR would be used for?
Yes,
Or mainly
so yeah, near IR can also be used for also identification, but it doesn't have sharp peaks, so it have overtones more, but it can also be used for a quantification as well. So there are a lot of NIR instruments that get calibrated to determine composition in different samples. For example, I used to work at a flour mill in the R&D department many years ago, right after my master's degree. And one of the things we used to do daily is get a flour sample from the mill and look at ash content, protein content, fat content. It's part of the specification to the quality. If the ash content is high, there's something off with the refining process. So we know that there's something off. So instead of ashing, that means trying to put the sample in a muffle oven and then get the answer the next day. You want to know now during production if there's anything wrong with the refinement. So NIR is the instrument of use.
Thanks.
I saw Tekiro for a minute and then he left.
Oh, that was Sammy. Sammy just got done with his Zoom link. And so they'll do a Zoom link and then they'll get about 15 to 20 minutes to work on stuff alone. And then they'll go back to a Zoom link. And so he's on break for the next few minutes.
Any other questions related to this sample exam as you go through it?
I have a lot to study, but I don't have any more questions.
Okay, that's fine. So tomorrow I have my office hour again at 8. So if you have any additional questions, I will also be on my in my Zoom meeting room. Otherwise, if you have any questions via email, I'll try to answer, but you probably won't get answer from me until the evening because I have meetings all day today. But yeah, I'll try to respond to your emails.
Thank you for doing this.
Yes, of course. You're welcome.
Thank you.
Good luck and don't panic too much. If you know your lab material and you followed lecture material, it's fine. You don't have to over stress. So I think you'll be okay. All right,
Bye now.
bye.